So we're happy to start our last talk of the workshop by Qianyu Hao, and she's going to talk about exact WKB of solutions by Borel summation and TBS.
Thank you for the introduction, and I want to thank the organizers again for organizing this wonderful workshop. It's always a pleasure to be here, and thank you for the opportunity to speak in the conference. So I'm going to describe my work in progress on the exact WKB methods of solutions to the differential equation by Borel summation and the open TBA equations. So this work is in the framework of the very useful correspondence between the 4D n equals 2 theory and the differential equations. And here on the supersymmetric field theory side, we need to insert some surface defects because actually this variable of the differential equation is a coordinate on the moduli space of such surface defects. And this correspondence include all kinds of different supersymmetric theories and differential equations of different ranks. But here I'm going to focus on the simplest case where the differential equation is a second-order ordinary differential equation of Schrödinger type, which is written here. So this correspondence is actually a very fruitful research area, and lots of people have contributed to developing the dictionary between the two sides. Include lots of audiences here. And in my talk, I'm going to tell you about some new entries in this dictionary, which are closely related to the BPS states of the supersymmetric field theories. So to start with, I want to give you a quick introduction on how do we see that the differential equation can show up from the supersymmetric field theories. There are actually different explanations on this topic, but here I'm going to take a particular approach, and this is going to be helpful for us to understand the TBA equation later. So we can think about a particular type of 4D n equals 2 series of class S, where S stands for 6. Those theories are obtained by compactifying some supersymmetric 6D theory on a Riemann surface C. After doing so, you can further do a compactification on another circle, which has radius R, and this will allow you to go to some 3D n equals 4 supersymmetric theory, where it has a nice target space, which is hyperkähler. And actually, this hyperkähler moduli space for the 3D theory is also identified with another interesting moduli space of the Hitchin's equations, and from there, we can get a flat connection directly in the setup as following. So we know that for the moduli space of Hitchin's equation, because it's hyperkähler, so there is a CP1 of the complex structure. And for each such complex structure, which we call zeta, we can construct a flat connection using the solutions to the Hitchin's equations. And this ensures that the connection is flat. And this solution contains a G connection A in the G bundle E over the Riemann surface, and a Higgs field phi, which is a one-form valued in the endomorphism of this bundle E. And having this flat connection, we can actually study some interesting limits where the parameters are set to 0, where we set both the radius R and this complex structure to 0. So this limit is usually known as the conformal limit, and we keep the ratio of these two things to be finite and denoted by epsilon, and this epsilon will be this quantum parameter showing up in the Schrödinger equation. So in this limit, if we study the flat section, it becomes an OPER, which has this expression where PZ is determined by the theory and it's some meromorphic quadratic differential. And after we have such an OPER and study its flat connection, it's straightforward to pass from it to a second-order ODE that we would like to study in this talk by going to the one-jet bundle formed by the solution and the derivative of it. So this is a standard maneuver to go from a first-order rank 2 differential equation to a second-order ODE. And actually, there is a more intuitive and direct way to also see that such a differential equation can show up, which is we can study the Separator curve corresponding to the infrared physics of the 40N equals 2 theory, which is given by this sigma here. It lives in the cotangent bundle of this Riemann surface C, and if we choose the coordinates on the fiber and the base to be x and z respectively, it has this form of x squared plus pz equals 0. So if we now lift x and z to operators and require their commutator to be I epsilon, we can get this quantized version of it, which is also this second order ODE that we would like to use. And here, just to say a little bit more about the details of this sigma, it's actually a 2-to-1 cover of the Riemann surface C because of the square here. And for each point Z on this Riemann surface, there are two preimages of it coming from the square root of this expression. Okay, so now I give you some quick idea why we would have such a second order ODE from the supersymmetric field theory. We can temporarily forget about this connection and just look at the ODE itself for now.
Does epsilon appears also in P or not?
I
think no.
So for it depends. For the theory like a Mathieu equation corresponding to SU2, there is this extra term epsilon squared over 4. But I want to simplify the discussion. Here I'm just using PZ. Okay. So if we just have such a Schrödinger equation, we know that it's in general hard to find a closed form solution for it. And in the quantum mechanics class, there is this WKB approximation where we employ an WKB ansatz given by this exponential of 1 over the quantum parameter and the integral of some y, which is a formal series in epsilon. And what we did in the quantum mechanics class is that we are truncating this series because this series is some asymptotic series with the coefficient diverge n-factorially. And there, by using finite terms, we can already make some useful conclusion from the study. And actually, there is something we can do more than that, where we need to use the order WKB expansion, where we use this whole series. And now let me first tell you how to obtain those coefficients for this series. So if we substitute this WKB ansatz into the ODE, we can find a quadratic equation satisfied by the y appearing in this exponential. And this equation satisfied by it is usually referred to as the Riccati equation. If we look at the classical part of it, which corresponds to epsilon equals 0, we will get an equation y0 squared, and this term will disappear because it depends on epsilon, equals pz. So if you solve for this classical level equation, you will get a square root with this ambiguity of the sign. And actually, if we choose a sign here, this will determine all the higher order terms, yn, in this series. And eventually, this will determine which solution we are studying. So we will label the solution psi also by a label given by 1 and 2, representing whether we take plus or minus sign for this square root. And this I equals 1 and 2 are actually a result because we are studying second order ODE, so the solution space is actually 2 dimensions. So they give a basis of the solution. Okay, so now we have this asymptotic series where we can calculate all the coefficients. There is actually the network developed by the exact WKB community, which can actually produce something exact, which serves as the actual solutions from this asymptotic series. This story starts with the Borel summation, which I'm going to introduce shortly. And after the Borel summation, there are also other techniques developed for getting some exact result here, which might not directly using this series, but it's using certain properties of the series. For example, there is the TBA equations, which I'm going to introduce. And there is also other exact WKB method that I'm not going to talk about in this talk, but important. For example, there is the Nekrasov-Shadashvili partition function with the insertion of surface defect. This method is using a computable partition function in this supersymmetric field theory, which can be generated systematically using the instanton calculus. And the advantage of it is that in this expression, it's already exact in epsilon. I will comment a little bit more on this later.
Excuse me.
Yes.
Actually, there are of course techniques, actually ideas, a lot before Gayotto, Moore, and Nietzsche to derive TBA without any mention to WKB.
You mean this ODEM correspondence?
Well, as you wish, but it has been developed enormously yet.
Yes.
And, yeah.
I agree.
So you don't need any WKB for sure.
Yes, but here I'm more like talking about. This is my starting point, so I want to just mention it as an exact WKB method.
Yeah, but at the end you should at least check that TBA is the same as been derived before.
Okay, thank you for the comment. Okay, so here's the outline of my talk. I will first give a quick introduction to the Borel summation, and then I will also tell you about the Gayotto-Moore-Nietzsche open TBA equations. So in the discussion, I will use some specific example for the explanation and show some results corresponding to it. And at last, I will comment on some interesting future directions to go. Okay, so I want to start with this more familiar object, the Borel summation. So here, I want to first clarify some subtlety here, which is, so here we write down again the WKB ansatz for the solution, where we have an asymptotic series in the middle. So one thing is that you can, of course, apply the exact WKB method here and ideally, you can get some exact result, and then you do the integral of it. But in practice, this is actually quite hard because the Ricardo equation is nonlinear, so it's in general hard to find such a summation. So what we can do instead is to first take the integral of each individual coefficient, and then study the new series of this formed by those integrals. And then there is still a subtlety, which is this initial point of the integral z0. Because you can think about it like if we just focus on this differential equation with respect to z, then z is the variable there, and z0 is more like a parameter or initial condition. However, they are actually not that different. For example, you can also write down some differential equation with respect to z0. So it's more like you will have two copies of effects if you don't choose z0 carefully. And in the exact WKB community, what usually they use is to choose a branch point as this initial point. And this will simplify the discussion a little bit. And the branch point here, this B0, is denoted by this orange cross on the base, where it corresponds to, on the top, the two sheets of this double cover collide. However, even with this choice of branch point, there's still some problem, which is those YNs for n larger than 1 diverge at this branch point, and also their integrals. So in order to actually using this definition, we should also apply some regularization for this divergence. And the way this is handled is to define a regularization of this integral contour, and what causes the problem is this B0 point by going through a little loop around it. Because there is this square root branch cut here, when you go through a loop here, you are actually landing on the other sheet of this square root branch cut. And we know that they're related by some relation like plus minus sign. So this is like two copies of what we want for this regularization. So we need to further apply a factor of 1/2 in this regularization. And actually, this path, which is one chain on the several Wilson curve with boundaries at the left of this point Z, to different sheets of sigma has some physical meaning as the charge which grades the soliton living on the 2D surface defect in this coupled 2D 4D system. And such a soliton is very similar to the soliton living in a pure 2D theory, which is a BPS configuration interpolating between different vacua. And actually, the different vacua here are the different sheets of sigma. So this story is consistent there. So now I want to give it a new label for this new series obtained by doing the integral first and using this particular regularization. And I will call it curly Y. And here also the solution, which is the exponential of this thing, I will give it a special notation, which is this psi, capital psi. Yes?
B0 is not branch.
So
in what, meaning B0 is a branch point if the turning point is a simple turning point or an odd turning point. What if it's an even type turning point?
What is a even type turning point?
It's when the square root of the S naught, the Y naught, is squared with limit.
But then it's not a branch point, right?
But there's potentials where you don't have a branch point. You have, that's what I mean. So the branch point comes when you have odd numbers of Stokes lines coming out, but you have even numbers. So do you have a similar interpretation for these cases?
I didn't think about it yet, but in the exact WKB community, there are two things usually people do. One is to use the regularization at the branch point. One is use some regularization at singular points. I think in that case, they would use singular points as a regularization.
So it's a zero of Y0, not both, right? So B0 is a zero of Y0, right?
A0?
Zero P.
Yes.
Yeah, but I think she's assumed she's working with generic spectrum first, so all the zeros are simple zeros. Maybe you're asking about
double zeros. Yeah.
No. Yeah, yeah, but I think like this whole story is assuming generic spectrum, simple zeros, simple summation.
Yeah.
So you can take limits.
Okay, so now with this, we want to study this series coming from the integrals, and it's again an asymptotic series which has this factorially divergence behavior. So we also need to apply the exact WKB method to them. And here, let me first introduce the Borel summation, which will be denoted by S of this asymptotic series. So the Borel summation contains two steps. Yes?
Just briefly go to the previous slide.
Yes.
So I can see it. Okay, thank you. You can continue.
So the first step is to take a Borel transform. Because this original series is diverging n factorially, if we divide every coefficient by n factorial, we can actually obtain some convergence series with non-zero radius of convergence. And the second step of the Borel summation is to take a Laplace transform. This is the familiar form, and I want to emphasize that the integral contour for this Laplace transform depends on the argument of epsilon. And here is this term, e to the minus theta over epsilon for the Laplace transform. Those two things, you can actually check formally that they are the inverse of each other. And another thing I want to mention is that, so this by can have singularities. And we can see from this expression of the Borel, of the Laplace transform, that if by has singularities and it happens to lie on this integral contour, this will cause some problem. So it's not Borel summable. But however, we can still study some lateral Borel transform, lateral Borel summation, which I will mention later, which is more like we are varying this integral contour a little bit, and then such singularities will cause some discontinuities of the Borel summation. And such a contribution as discontinuities is actually non-perturbative because, for example, if we think about this thing has a pole, And we will pick up a residue, which is given by e to the minus theta or epsilon, which is a non-perturbative effect in epsilon. So actually, the singularities and the discontinuities are going to be the main object I'm talking about in this part of the Borel summation. So for explaining these things more clearly, I'm going to choose a particular simple example, which is the Weber equation, or a harmonic oscillator, but here we are studying off-shell solution. We don't study the quantization condition. And we can check the Borel plane for this Borel transform, as we said before, if we want to study the singularities. However, this is in general a very hard task to do. And what we can do is to use some approximation method to approximate the singularities. And one such method is petty approximation, where we truncate this series in the Borel transform and represent this truncated series by a rational function. And then we can study the poles of this rational function. And here are some examples of this petty Borel study of the Borel plane. And as we can see, those blue dots are the poles, which are the singularities of this petty approximation. And actually, they are not all of those poles have physical meaning. Usually, they form those series of poles, and we only look at the first pole in each of such series, and they give the approximation of the singularities.
How do you choose how to truncate the series, the asymptotic series?
Usually, you.
And then, if I understood correctly, on that you use the Padé approximation.
Yes. You can truncate the series by, in principle, any term. But if you want to have some nice behavior that gives you the prediction to the singularity, you need to use enough of them. Usually, I think at an amount between, for example, 60 to 100, this is already enough to see those singularities.
In such a way that the singularities have some real physical meaning, because this is the problem, no?
Yes, so
this is still an approximation.
Yes, this is only a approximation, and you can only say like you can only see poles in this petty approximation because it's a rational function. But the singularity that it wants to approximate is actually more complicated, and I think I didn't see proofs of this, and I don't know how to prove it. But I think people have been discussing that the singularities you want to see for those examples are actually branch cuts. That's why there are this series of poles, which gives you some branch cut behavior. And the only point which has this physical meaning is actually the beginning point in this case.
Yes, although you may agree with me, I hope that so you are trying to understand a cut using some pole approximation.
Yes.
Is that correct?
Yes. And as I'm going to talk about now, I will give you some description of those singularities in terms of the physics quantities. Okay, so here I'm giving two examples of the Borel plane corresponding to different value of z. We can see in those two pictures that there are two types of singularities. One is this one in the middle. If you move z on this parameter on this variable space of your differential equation, their position changes. Like from here is closer to the zero, and that one is further away. And there is another type of the singularity, which are those two. So here I'm not using enoughly many terms, so it seems to be a little off from the imaginary axis, but it's actually they're actually both on the imaginary axis, and they don't change positions when you vary this z. Okay, so now we are going to look at those two types of singularities respectively. The first one is this one, circle by this red circle. So this type of pole actually also appears if we don't study the series coming from the integrals, but the original series for the integrand appearing in the WKB ansatz. And in our work with Gracia and Naisky, we find that this position of the singularity should have the physical meaning of the negative central charge of the solitons, which we have just introduced as this BPS state, living on the surface defect of the coupled 2D4D system. And the central charge of it is defined using this charge we set that grade the soliton space as the integral over it of y0. And in my work, I'm studying a slightly different series, which is the integral of this those y's, and I find exactly the same thing of those singularities. And of course, it's natural to use the same explanation of them as the negative central charge of the gamma soliton. So here, those negative signs are just like a convention. Okay, and actually there is a more familiar language for describing these singularities, which is the Stokes phenomenon. So in Stokes phenomenon, we have Stokes curve defined by this condition. They are consisting of Stokes curve which are trajectories on this Riemann surface C, such that the corresponding soliton central charge, the negative of it, has the argument exactly as the argument of epsilon, which we use as a parameter for this Stokes graph. And what we know from the Stokes phenomenon is that the Stokes graph corresponds to where the solution has the Borel summation of the solution has discontinuity. And actually, we can see already that this condition defining the Stokes graph is exactly what we want for the singularity and discontinuities using this exact WKB language, because argument of epsilon controls the integral direction, and this controls the pole on the Borel plane. So this statement is exactly that when the integral contour of your Laplace transform meet some pole on the some singularity on the Borel plane. And actually, with this prediction of the singularity at minus central charge of the soliton, there's even more things we can say, or in other way, there's an intuitive way to check this statement, which is we also can say something about the length of the Stokes curve, which is where we define a cutoff version of the Stokes curve by this cutoff energy lambda. And here we require that when we form those Stokes lines, Stokes curves, it satisfies some condition on the absolute value of the soliton central charge. And here we have the argument, and here we have the absolute value. So in this case, to check the statement that the singularities are at the negative soliton central charges, it is enough to check that if we plot the corresponding point Z as the red dot on the Riemann surface, there will be a Stokes curve which ends at this exact point if we use the cutoff energy as this one. And here is the check for the Weber equation of these two different values of Z. And for each of them, we see that these Stokes curves exactly end at this red dot. So this is some check of the singularity at the soliton central charge. Now I'm going to talk about the other type of singularities corresponding to those not moving on the imaginary axis in this example.
Sorry.
Yes.
Can you go back? What are the red dots in the Stokes graph?
Yeah, so this red dot is this point Z equals this thing.
But that was a choice.
So the
Borel plane, right?
This is the Borel plane for this point, because this series is in epsilon, but Z is like a parameter there. So for different Z, you get different Borel plane.
So okay, but you have several red points.
Here?
In the Stokes graph.
There is those are orange points. Sorry, they are the branch points, and this is the only red dot. The Stokes graph is on Riemann surface C.
Yeah.
Right.
So that the red dot on the Stokes graph is like, is it the point where you're evaluating the solution of the differential equation?
Yes. So like we have this series y, right? Like, and it's a series in both it's a series in epsilon, but it depends on both z and epsilon. So if you want to study the Borel plane corresponding to epsilon, you can fix a point z of this series and study the Borel transform of it.
And you fix it on a Stokes line.
I can choose arbitrary z. And this statement of the singularity at the central charge of the soliton tells you that there will be a Stokes line going, and we are using the cutoff version of it, which uses this information of the absolute value of the singularity. Then there will be a Stokes curve which ends exactly at this point. So this is just a graphic check for this statement.
What was the value of epsilon that you used?
The value of epsilon?
That you used for the Stokes graph?
Yes, it has to be the argument of epsilon. So it has to be when this jumps happens. Yeah. Okay.
And you should be able to also do the Stokes coefficient as the law of connection coefficient for this point that moves around.
I'm going to talk about that later. So now I'm just going to first tell you about a little bit about the position of the singularities, and later I will tell you about the discontinuity. Thank you. So now we are moving to the other type of singularities, which are fixed when we vary this z. And the prediction, the proposal I made is that they should be at the negative central charge of the 4D BPS states. And there's some subtlety which I will discuss later. Basically, it involves some intersection number. And here, let me first tell you what is this gamma here. So this gamma should be some one cycle on this Sebold curve sigma, which graded the 4D BPS states. And the corresponding central charge is defined as usual as the integral of y0, which is just square root of p, over this loop gamma. And actually, this is the classical part of another very interesting quantity, which is the quantum period. And the quantum period is just to replace this y0 by this y in all those integrals. And sorry, there is an exponential of this. So now I have told you that there will be those singularities at the 4D BPS states. Let's check that in this simple example of the Weber equation. So in the Weber equation, actually a way to get the BPS spectrum is to also use this Stokes graph, and the 4D BPS states will show up as the degenerate type of Stokes graph, in the sense that we're, just as you mentioned earlier, we are using all the simple type of branch points here. So there are 3 trajectories coming out of each of them. And the degenerate Stokes graph has some segments like this, which consists of a Stokes curve coming from the left branch point and then another Stokes curve coming from the right branch point and sitting on top of each other. You can think about they are going like head to head each other and form just this kind of segment. And we can deform this kind of, is usually referred to as the saddle connection, to an actual one cycle on this Riemann surface, on this Sebold curve sigma. And this is the charge gamma that we have for this BPS states. And in this Weber equation case, we can just check the Stokes graph for different phases and see that there is only one BPS state here, which is the flavor hypermultiplet. And we can calculate explicitly the central charge of it, which is minus 2pi I. And we can see that this, and there is also the antiparticle of that, which gives you plus 2pi I. So we can see that these are approximately the points we get in the Borel plane.
So now Z is the integral around the cut.
Yes. So actually, in this case, there are only two branch points, so it's equivalent to the circle around infinity. That's why it just pick up the residue here, which is minus 2 pi I.
The residue at infinity or the cycle around the cut.
They're the same. It's a CP1. Yeah. So, and actually in this case, I want to mention that the quantum period is not subject to quantum corrections because basically the sigma is a genus zero surface. And if you are familiar with this subject, and it's just given by e to the g gamma f over epsilon. Okay. So here I just described the positions of the singularities, and now I'm going to discuss maybe the more interesting discontinuities corresponding to them.
But you call this quantum period because of the gauge theory, not because of the quantum mechanics, because this is the classical contribution.
So, this, like, I'm still using the definition with the quantized version. It's just in this example, it has no contribution from those epsilons, because it's basically just this.
In general, you would have to get the exact Y solution.
The exact Y solution?
Yeah. So, yeah. In general, your ambition would be to integrate around this closed path, this closed the exact Y solution.
Yes. In general, it should be this, but in this case, because just as you said, this cycle is like equivalent to a cycle around only this puncture at infinity, so it doesn't have those quantum corrections.
It doesn't have epsilon corrections.
Yes. That's why this example is especially simple.
Okay.
Okay. So now, maybe more interesting. The more interesting topic is the discontinuities corresponding to those singularities. And here I'm going to define the lateral Borel summation we have mentioned before in the case when when the quantity is not Borel summable. And we can think about that. So here, first of all, in this Laplace transform, I have this integral contour controlled by argument of epsilon. If I have some poles lying on this integral contour, I can think about slightly deforming the contour to slightly above and below this pole, which is given by this plus minus sign. And I call the quantity defined this way as the lateral Borel summation. And the discontinuities will be given by the difference of those lateral Borel summation, as we expected. And here I define two types of discontinuities because we have two types of singularities. Their discontinuity behaviors are slightly different. For one of them, it's like the difference is in the exponential level, and for one of them is like the difference in psi. Or in other words, if you want to use psi for both of them, one is like taking the difference of Borel summation, the other is like taking the ratio of the two Borel summation.
But these are the Dalabert-Pham discontinuity equation.
If you study quantum periods and the lateral Borel of quantum periods, I think that's the level.
Because you are
like now I'm studying like the solutions.
Somehow these are these are the discontinuity of the wave function of the
yes.
Okay, yes.
But you will see there are some very similar components later.
Yes, exactly. Then you have to translate this into the discontinuity of the
yes.
the period. Actually, of the Y of the TBA.
Yes.
TBA solves the equation.
Yes. Yes, that's exactly the idea.
Yes.
So, yeah. So here, let's look first at these singularities as the BPS central charges. And here, actually, there's an even simpler example we can use, which is the area function, also known as the Stokes equation, which is where this whole Stokes phenomenon story starts. And there, we know that there's some Stokes graph corresponding to it, and the solution for the area function has this discontinuity behavior that the discontinuity of psi 1 is given by psi 2, and psi 2 is given by psi 1. Here I want to use, and exactly at this kind of condition giving the Stokes graph. And here I'm going to formulate it in another way, which I think is neater, which is we can use the solutions, the two WKB solutions have symmetries with epsilon goes to minus epsilon, subject to an overall factor I. So if I use this symmetry of the second order ODE, I can write the discontinuity of psi just by itself with epsilon replaced by minus epsilon times Ni. And this is the simplest case. And in my work, I'm giving a proposal for the generic type of discontinuities for arbitrary examples. And here we are using the quantities coming from the physics part. So again, at this particular case, where argument of epsilon equals argument of negative central charge of the soliton, the discontinuity should be given by the following ingredients. The first one is a counting of the BPS soliton, which is usually known as the BPS soliton degeneracy. And we still have this factor we have seen for the from the array function, I phi minus epsilon. And then there is another case which comes from which has so here I want to first mention that for a generic theory, you will get different numbers of branch points instead of just one. So there might be some the problem you won't experience in array function, which is there are different types of solitons. For example, here for the Weber equation, you can draw a soliton surrounding this point or another soliton surrounding the other point. So in this case, we will need to label them differently. So there is that's where this subscription I coming from, and we need to define a quantity which is the difference of the two soliton, because we can only use one of them for regularization of the solution. And now, if we are studying the discontinuity caused by the other one, there will be some contribution coming from the difference of them, which is defined by a concatenation of the two paths. Basically, if we take gamma soliton 2 here, so this minus sign only reverses the direction of how this open paths go. So if we reverse this direction, gamma soliton 2 minus gamma soliton 1 will just give you one cycle on this Separating curve, and then we can calculate the intersection number of this one cycle you just get, and this gamma is a 4D BPS charge, so you can calculate the this quantity just by the intersection number. And this omega here is the counting of the 4D BPS states, which is known as the 4D BPS index. And there is another more complicated expression, which is this integral term, which has quantum period as part of it. So this is the generic proposal for the discontinuities for arbitrary corresponding to arbitrary soliton central charge. And actually, we can do some check of this proposal numerically. And here is a check in the actually not in the Weber equation example, because if we want to see this kind of non-trivial contribution from this more complicated term, we need a non-zero intersection number of gammas, which are one cycles. So we need a Separating curve of at least genus 1. So the Weber equation doesn't work because it's of genus 0. And we have to go to a more complicated one where we used the modified material corresponding to the pure SU2 theory. So in this case, all those terms.
Cosh potential, just to be concrete.
Yes. And here, actually, we used a change of coordinate to go to from E to the X to X.
Okay.
Yeah, that's just the details. And then I want to mention this because if you do this change of variable from modified material to this other variable, you will see this extra epsilon over 4 term coming up from the change of variable. That's what you asked in the beginning about whether this potential term has any epsilon dependence.
Okay. Yes,
yeah.
yes. Yeah, but from the point of view of integrability, quantum integrability, it doesn't make any difference where epsilon is. It can be everywhere.
Yeah. And here are some numerical checks of this proposal mentioned before, and here on the left column, we are calculated using the difference of letter of Borel, and on the right-hand side, we are using this proposed expression, and we see pretty good matching. And here we chose some specific value of z. And the two solitons here is drawn below. One corresponds to a soliton connecting the branch point on the top, and one corresponds to a soliton connecting the branch point at the bottom. Yes.
So this continuity. So can you explain a bit more? So here you're in terms of the differential equation, you have the Stokes line, and now you're taking the discontinuity across what's
Yeah. So there are two ways to think about this problem. Basically, in this Borel summation method, you have this Borel plane, and let's say you have some singularity here. So and the case where it is not Borel summable corresponds to like your integral contour directly going through it, right? But there are two ways to see this discontinuity. One is that you are keeping this integral direction fixed.
Now you are in the Borel
yes.
variable.
Yes. So there are two ways to see this kind of discontinuity. One is you vary your z, and this kind of soliton central charge will change, which means the pole position will change, for example, from here to here. And then you have the discontinuity. And the other way to think about it is to keep this choice of z and vary epsilon, because then it will change the integral direction. So they are actually equivalent to each other. And in my definition of the discontinuity, it's more like this discontinuity, but you can easily translate it to this kind of these other types of discontinuity.
So the picture on the right, isn't it just the Morse direction for when you cross the Stokes line? Like I mean, in the Stokes plane, the picture on the right would be you keep fixed the Stokes graph and you
this one
across the Stokes line.
Yes.
That's what it is. But isn't that the Morse direction formula? Exactly. It tells you how the wave function down.
I'm not sure.
The Morse connection formula are when basically you have coalescence. So basically, it's when you have Stokes lines that are connecting turning points. Right?
No, that's the Delaunay-Dillinger form.
Okay, so then when you're talking about connection, so that's yeah, then that is it. But those two things, meaning what she wrote there, they're exactly the same thing.
Yeah,
and
it's the
it's
one
exactly
on the right
that.
is the Stokes connection, but it's what happens.
And the previous formula that she has in the previous, it's the DDP formula, but just interpreted, I guess, in a different language. But it is.
Yeah, I would like to know more about that maybe after the talk. Thank you. Okay, so now we can talk about sorry, let me see. Yes, the other type of discontinuity, which is even more closer to the conservation summation transformation. And this corresponds to these other types of singularities, which are at the negative central charges of the 4D BPS states. And here, let's go back to the Weber equation we started the discussion with. And there, it has been proven that the discontinuity of y at this particular condition is given by plus minus 1/2 of log 1 plus x minus plus gamma f, depending on whether you use plus gamma f or negative gamma f there. And we can also check numerically that there is this pretty good matching of the quantities at different points of z and at the central charge of gamma f and central charge of negative gamma f, respectively. And more generically, the proposal for this discontinuity is again expressed in terms of the quantities appearing in physics, where we have the intersection number of the soliton you used to regularize your solution, and gamma, which is the 4D BPS state charge that you are considering the discontinuity at. And here is this term log 1 minus, where sigma is some quadratic refinement. Basically, it is either 1 or minus 2, whether 1 or minus 1, depending on which type of, whether it's vector multiplet or hypermultiplet, the BPS state. So this expression actually is 1/2 of the conservative Subelman transformation. But we can also understand this because in our regularization, we kind of just use the square root of this quantum open path integral for the soliton charge. And it has been studied that for such quantum open path integral, it's subject to same types of conservative Subelman jumps, but with the intersection number replaced by the charge of soliton with gamma. And here is natural that we see this kind of 1/2 jump of the conservative Subelman type. Okay, so this is what I want to say about the Borel summation side. And of course, we can apply Borel summation to arbitrary points that is Borel summable and do some calculations. But let me leave that part to later and first tell you a little bit, yes? Okay, about the GMN open TBA. So in short, the GMN open TBA equations is a conjectured thermal best ended-like integral equations, which is satisfied by a function g epsilon, which has this expression, which solves some Riemann-Hilbert problem where the asymptotics is given by just the first term here, because the second term depends on epsilon. So more or less, you can think about that. It goes away when epsilon goes to 0 for this asymptotic. And it is also, this g epsilon for this integral equation is also piecewise analytic, because as we can see, there is this epsilon prime minus epsilon term here. So if epsilon is lying on the integral contour of epsilon prime, this is a pole, and you will pick up the residue of it, which is exactly given by the expression down there for as the discontinuity when you either change the integral contour. Here I want to mention quickly, like, where does this open TBA equation originally come from? And I want to go back to this explanation in the introduction on why we would like to, why we could see second order ODE from the 4D_2 theory by going to the 3D_4 supersymmetric field theory with target space hyperkähler manifold. And here we mentioned that this flat connection is responsible for producing this second order ODE in the classical limit, in the conformal limit. And here actually the G has a definite meaning here, which is that it is just the gauge transformation which diagonalizes this flat connection even before the conformal limit. And here GMN made some conjectures on how this GI and this AI, which is like now the eigenvalues of this flat connection, should behave using the knowledge from the physics side of the wall crossing of the coupled 2D/4D system. And they write down the following expression for them. So this is still the expression before taking this conformal limit. And this x gamma ji is related to the little case ai here by this differential relation. And then if we apply the conformal limit, this becomes exactly the integral equation in the on the formal page. And here we are more interested in knowing how those two exact WKB methods are related to each other. And here I want to say a few more words about this, which is we can still employ this kind of gauge transformation in the conformal limit where we have this flat section of the flat connection. And we mentioned in the introduction that this flat section is just the one-jet bundle of the differential equation solution. So in that case, I'm going to be a little sloppy here. So this psi I is basically this one-jet bundle, but since the two components are related, we can also think about this as the solution itself for the differential equation. And here we can do the same trick as before of diagonalizing A in this conformal limit by this GI, where we redefine this flat section by some other function times GI. And in this case, using the explicit expression of all those quantities, we can find out the equation satisfied by this little case phi I, which relates the TBA result with the kind of the Borel summation result. And this is an equation that is solved by this kind of expression by taking the integral of AI in the exponential. And in this case, there's actually also some ambiguities about regularization and normalization. To match the two results, we choose the same normalization as before and get this expression of it. So this is basically because in the expression of AI, so this is still before the conformal limit, but we can see that it has this dependence on some integral expression, which will become this expression depending on this integral here. And we propose that this is what we need to connect the two methods together. So here, with this bridge, we can do some check of the matching of the two methods. And here, I want to show you quickly some numerical result for the Weber's equation, which is just this one. The first three rows here are the numerical calculation using the TBA methods, and we are varying some parameter for this calculation because we are just using the iteration. So we are adjusting like the steps and the cutoff place for this integral calculation. And we see that they are converging to the Petit-Borel result obtained on the exact WKB side. And actually, there is also some check for the pure SU2 theory in the strong coupling region, but it's not working as well as here. So actually, this is related to some future direction I want to discuss. It's because the numerics, especially for the TBA equation, are in general quite complicated. You are solving some coupled integral equations together, and because of this term, here appearing in the integral equation, you even need the quantum period as some input if you want to solve for the TBA equation for the solution. So in the pure SU2 theory, so I don't have a very effective way to calculate the TBA result for this example, even though it would be, of course, very interesting if we can solve the modified Mathieu equation with this kind of new result. So a way to improve the numerics is highly desired. And one thought about this might be using some boundary condition at the other side of epsilon. So we use the asymptotic of epsilon goes to 0. But it would be nice to also have some boundary condition for epsilon goes to infinity. And such a boundary condition has been discussed for the closed TBA case, where they are studying the TBA equation for the quantum periods. For example, in the work by Grassi-Gu and Renew, it would be, and there the approach they take is to use some identification of the quantum period with the Fredholm determinant, and then further using some incidental calculus expression coming from some compactification from 5D to 4D. And here it will be nice if we can also find such a boundary condition to improve the accuracy.
But actually, you can make this limit on the TBA equation for the usual TBA for the quantum periods. Why not? I'm quite confused about what epsilon is in the spectral parameter language. Should be the exponential of it, but this is a limit. I think it's the so-called kink limit. You can compute from TBA equation for the quantum periods. The one you would call the closed TBA.
Yeah.
The TBA equations for the periods without Z. As far as I've understood, correct me if I'm wrong, you have written some equations, TBA-like equations for the wave function.
Yes.
Not for the not only for the periods, but also for the wave function.
Yes.
Could you put again the equation? So
this is not what I write. It's by Galto, so I'm German.
So, but this G of epsilon depends on Z.
Yes, sorry. Yeah, there's one important point, as you pointed out. They depends on Z, but the TBA equation is an integral equation with respect to epsilon. Okay. So I omitted that dependence.
Yeah, epsilon is the exponential of theta. You can find this also in the appendix of Gaiotto, Murray, and Niesky, in which they try to reproduce TBA equation in the idea classification by homological.
Yes.
But these are not that equations. Are the equation of homogeneous and order. Apart from this, the G is the wave function, isn't it?
G is not directly the wave function.
But it's related.
Yes, it's related. So it's related by another factor which depends on Z, because the solitary depends on Z. So it's not directly the wave function yet.
One is just the first component of the vector, isn't it?
Sorry. So this one, in the exact WKB part we introduced, there is this basis of solution.
Yes.
Side 1 and side 2. Yeah.
Yeah. That's okay. Now, what I wanted to say that you have equation for the period, TBA equation, not depending on Z, and you can do that limit on that equations.
But I'm not I know that for example, in this work by Grassi, Gu, and Marino, they exactly use this Zamenhof. Well, I don't think they is directly using, but it's related to that the quantum period satisfies this TBA and Fredholm determinant satisfies this Zamenhof of TBA. So they are kind of related, and they have some result for the boundary condition for the Fredholm determinant, and they used it to improve the TBA calculation of the quantum period. But if you happen to know some other,
I'm afraid that TBA equation tells you already this what we call asymptotics. If I have understood what you need, because you need just the behavior of the quantum periods from TBA.
Yes.
As an input, somehow, no? And then you need also the exact quantum period from TBA.
So
the issue that the massless conformal TBA admits several types of boundary conditions.
Yeah, but it goes like minus 4p theta, or theta going to minus infinity. Now epsilon is e to the theta problem. But anyhow, I don't want to interrupt you, but I think that can be elaborated. It's a zero mode of probability theory. It's nothing except to a point. It's very simple point.
Yeah, I would like to discuss more about this if you happen to have time afterwards. And actually, I think so. Maybe using your description is enough for improving this TBA method. But I still think it might also be useful to use this kind of universe of partition function approach for the wave function. And there it might tell you more because it's an exact function in epsilon. And there's some nice work already studying this kind of SU2 NF equals 0, 1, 2, 3, 4 theory by Professor Bonelli, Tanzini, and Cristoforo here, and also the other author. So it would be interesting to know more about this exact WKB method and see how it helps. And one another thing I want to mention is that TBA equations, as I said, even for the open equation, you need the closed quantum period as an input. And because we need to integrate it over the whole line, it's nice to also solve them by the TBA methods. So in principle, for solving TBA equations, you are solving a coupled system of TBA equations, and that depends on the BPS spectrum of your theory. Here, we are just exploring the strong coupling region where the BPS spectrum is finite. And there is also the weak coupling region where the BPS spectrum is infinite, and then you will have a coupled infinite numbers of integral equations. So it would be nice to also develop some technique for calculating the TBA equations in that region. And the last thing I want to mention is that there is this nice 4D equals 2 and differential equation correspondence. But there's also some generalizations of it already existing to the difference equation and 5D equals 1 theory correspondence. And for the difference equation, there are less results and studies that have already been done. So it would be interesting to generalize also this open TBA method to the difference equation. And there are some exact results are already obtained by the work of people. So it would be nice if we can compare the two constructions. And that's the end of my talk. Thank you very much for your attention.
There is a lot of questions, but there's still time for one more question if there's.
So let's ask, does it make sense to compute some ground scans of this wave functions computed by this TBA equation? Like, will they give some Q functions, which would also solve some equations?
What is Q function? Sorry.
It's Brownians. The ODE, right? It's the Brownians.
Yes, well, the same functions from parameters. So,
register that I didn't say anything.
Yeah. So if you are just saying about Wronskian, in my understanding, that usually happens when you go through the Stokes line, but there isn't the wave function like an input for the Wronskian.
Oh, they are inputs, but at the same time you are finding them in some way, and not Wronskian, not just Wronskian, but this wave function themselves.
I don't know about that, but I would like to talk about them with you more.
I know.
Yeah, I didn't think about that.
So I'd say that we should just thank all the speakers.